There is another type of growth model when it comes to populations of living things. Besides the exponential growth model, it's called the logistic growth model. And it's actually a more accurate model of populations that don't grow exponentially forever, that over time they have things that make the population settle down and stop growing. So it's called logistic growth or the logistic growth model. And it's an S-shaped curve. It starts off growing exponentially, but then about halfway through, it levels off, starts to level off, and hits a horizontal asymptote. Now, we call that horizontal asymptote the carrying capacity. Here, whatever population this is, if this is days along the horizontal axis, roughly around day 39 to 40, somewhere in there, this population ceases growing. In other words, there's about an even number of births and deaths in the population, and so the population ceases to grow. It levels off and it hits what's called its carrying capacity, and that's evidenced graphically by a horizontal asymptote to the graph. Here it looks like the carrying capacity of this population is 1,000. So exponential growth can't be sustained for long in any population. More realistic population limits the growth by incorporating the carrying capacity, usually delineated by the capital letter K, and it's the maximum population size the environment can support. In anything that is living on this planet, or even in a petri dish, there are limiting factors to the growth of that population. The size of their environment. In a petri dish, there's only so much space. The food supply available, the water supply available. If it's a moose or if it's a deer, predation has a big factor on the growth or the decline of that population. So when we have these limiting factors, the exponential growth is going to be slowed, and eventually the population will hit a stasis. Now, it doesn't mean that after how much ever time goes along, that population never has more births than it does deaths at any single time. It just means that it hovers back and forth, up and above and back and forth, this carrying capacity. But it will stay a little bit over or a little bit under this carrying capacity. It won't go way over it or way under it unless something drastic has happened to the environment. So in the logistic population growth model, the rate of increase declines as the carrying capacity is approached. So there you can clearly see the difference in exponential growth and the logistic growth model. So the reasons for decline in exponential growth of any population are those limiting factors such as environment, food supply, water supply, predation, and so on. Here's another graphical example of a population here of a paramecium hitting a limiting, due to limiting factors, hitting a carrying capacity that looks roughly about 900 individuals in a matter of about 10 to 12 days. So we can tell a lot about the growth and the slowing of the growth in the population basically from graphs. There is an equation that is the logistic growth model, but we're going to save that for our calculus work. We won't be dealing with the equation here in pre-calculus. We're going to be looking at a lot of graphs of populations that exhibit logistic growth and answering questions about that. So come to class tomorrow and we'll take a look at the graphs of logistic growth.